All right, we'll go ahead and get started. Hi, I'm Jen Rexford, and it's my pleasure to introduce Shaddi Hasan, who will be our lunchtime speaker at CITP today. He is an assistant professor of computer science at Virginia Tech, and he does research at the intersection of computer networking, human-centered computing, and information and communication technologies for development. Prior to going to Virginia Tech, he was a software engineer at Facebook Connectivity and a co-founder of a startup that was acquired by Facebook. Prior to that, he received his PhD from Berkeley in 2019. And I personally really enjoyed working with Shaddi over the past year on a project that he was heavily involved in at Facebook called Magma, an open source software platform. I've learned a lot from him about the unique challenges of developing networking technologies that can work in challenging regions. And he's going to talk to us about his work on lessons from the edge, what rural connectivity can teach us about networking. Thanks so much.
Yeah, thank you so much for the introduction. So it's wonderful to be here and have a chance to talk to all of you. Like Jen mentioned, my research kind of sits at this intersection of networks and a field called ICTD, or Information Communication Technologies for Development. And some of the research questions that my group kind of thinks about are how marginalized populations get access to and benefit from the internet, how we can build networks that scale well in hard to serve areas, and most recently, how we can think about how to measure where meaningful internet access is available. I already got this introduction, but I've had a variety of roles before I came to Virginia Tech, where I'm now an assistant professor working kind of on the startup side, working in big tech. But basically, since I began my PhD, I've been really interested in these questions around how we bring people online to a faster internet, especially in rural areas. So I want to start by kind of sharing kind of contextualizing where the world is at right now when it comes to availability of access to the internet. So this is a graphic from the GSM Association, which is the industry association for mobile network operators worldwide, that kind of charts the growth of mobile subscribers over time. And this particular one ends in 2020, but today, as of last time they kind of published data in 2021, there's about 5.3 billion unique subscribers to mobile services worldwide. And this is expected to grow to 5.7 billion by 2025. And so this is actually pretty good. Most people in the world are users of mobile networks. That's pretty impressive for a technology that didn't exist like 40 years ago. At the same time, the same industry association kind of has this claim that these networks, even as early as 2017, were reaching the limits of coverage within the footprint of an economically sustainable business model for traditional mobile network operators. So if we take them at face value, these networks are roughly reaching the limits of their growth in terms of the set of population that will be coverage. There's obviously gaps within that, and there's some projected growth still. But if you kind of do the math, kind of taking population in the world versus who is actually using the internet, there's about 1.7 billion people who are currently left off the internet in terms of access to mobile broadband coverage. This is not even including people who are thinking about affordability constraints. And there's 400 million people who live outside the footprint of any mobile coverage. So this means they can't send a text message or make a phone call even in the case of emergencies or something. And so one of the lessons I take away from this is that as a kind of society, we really know how to build large scale infrastructure that reaches most people. Like, it's amazing that cellular networks reach as many people as they do today. But this infrastructure will often systematically exclude people from underserved communities. And so the question that I'm curious about is how we can build systems that better serve these unserved edge cases. And when I was a student, I was describing this problem to Martin Casado, who some of you may know, and his response was, that sounds like a profoundly non-technical problem, which was like a little bit much to hear as a second-year PhD student in computer science. And over time, I think he's right in a lot of ways. Rural internet access is not a technical problem. There's a lot of work that goes into organizing communities and helping communities figure out the way in which they can improve their own access to infrastructure. But at the same time, the designs of our systems also kind of shape what's possible. And so there's certain values and assumptions that get embedded into the network systems we develop. We make assumptions about who's going to be using our system, what business models they're going to adopt. And to kind of borrow a phrase from Bruce Davey and Larry Peterson, I think it's useful to take a systems approach to connectivity access, particularly in rural areas, and ask the question, why are these people or places not served by today's networks? And start to surface some of the socio-technical context in which the digital divide exists. There are other aspirations and desires of users and communities, policy, financial considerations that goes into understanding why network places aren't covered. And my claim is that once we kind of understand what these socio-technical challenges are and start to recognize their existence in some cases, we can start to understand why traditional approaches don't work at the edge and start to design new systems that can. So let's take a quick look and see how the modern internet works. And so we can start to understand some of the challenges of where things fall apart. So as some of you may be familiar with, if you've taken a networks class before or worked on network systems, internet is a network of networks. Campuses like the one we're at here at Princeton will be ISPs on this network. You might connect to the internet through an ISP at your home. You might also connect to the internet through a mobile network operator who is also functioning as an ISP. And what we're going to be focusing on today are these mobile network operators, because I'll discuss in a moment. This is what really matters, especially when we're looking at how most people come online in the world. Most people are coming online through mobile devices. So this is kind of where the action is. And if we think about a modern cellular operator, when they're thinking about how they're going to upgrade their network to adopt kind of next generation cellular technologies to meet rising demands and so forth within places they already serve, particularly in emerging markets, which is where most of my research has been focused, they're going to be a large corporation that's part of a multinational kind of network operator group usually. They're going to be building nation scale networks that are aiming to serve most people within that country. And they're not really tech companies in the sense that they don't have a lot of engineering capability. They're heavily reliant on their vendors to be able to kind of determine what's possible and what their cost structure is going to look like. And so given they also have limited capital and like everything else, they face opportunity costs. When they make these decisions about where they're going to build next generation networks and do upgrades, they're weighing these trade-offs between whether they're going to continue investing in areas where they already have service that have clearly been profitable already, or are they going to try to do something different at the edge. And what this means is that we often are going to see these companies just not invest in rural areas. And this is played out in other contexts as well. We can look at even the history of telephony in this country. Hopefully folks are familiar that AT&T used to be the incumbent monopoly that provided phone service within the United States. And they provided truly state-of-the-art service for most of the United States throughout their existence as a monopoly from the 1870s until 1990s, I think, something like that, maybe a little earlier. And at their, this is an example of what their network looks like in 1970. And I think this is kind of like the heyday in some sense of the AT&T monopoly network. And even at this point, 13% of Americans didn't have access to a phone in their household. And in some states, particularly in the South, this could reach as high as 32% in 1970, nearly 100 years after the founding of the Bell system. And so while most of the country had really reliable state-of-the-art phone service, there were still gaps at the edge. And what this meant is that rural communities would have to kind of come up with new innovative ways to make sure that they could get service on their terms. And this could range from different kind of technical approaches, such as using kind of the barbed wire fencing on ranch lands to provide last mile phone service because it was already existing infrastructure in the ground, to kind of innovative financial and kind of business operational models like the formation of utility co-ops that could allow communities to pool their resources and put the investment necessary in to provide service for themselves, even if it wasn't financially attractive to the existing carriers. And we still see this playing out today with the internet infrastructure. So we can take a look at a modern example in Peru, which is where I had done some of the work that I'll be talking about in this discussion. And for those of you familiar with Peru, a lot of the population lives near the coast of the country, pretty heavily centralized in the capital of Lima. And if you drive kind of north and east, you'll get over the Andes and into the Peruvian Amazon. And one of the last towns you'll encounter is this town of Pucallpa. And to the southeast of Pucallpa, where the work that I did was taking place, there's basically no cellular service, very limited internet access, and so forth. And if you're an infrastructure nerd like I am, and you go to Pucallpa, what you'll notice is it has like far more radio towers than any town of its size deserves to have. And this is because this is where the road ends, and that's where the fiber network ends, and this is the end of traditional network infrastructure. And so if you go to the edge of town, you'll see lots of little towers like this sitting in people's backyards, and they're actually small ISPs that are using wireless technologies to provide service to rural communities beyond where the road network is. And so this particular tower was part of a series of relay stations that was sending service to this town in Puerto Bermudez, about 200 kilometers away, where they were providing the only form of internet or broadband, in quotes here, service in this particular location. And their central office for this ISP looked something like this. This is where all the traffic for all the towns that they served went back to, at the base of that tower that I showed you a picture of. And I would make the claim that this is kind of a really innovative approach to providing internet access at the edge. This is what a lot of networks are going to look like, where we're talking about if we want to provide sustainable service to that 1.7 billion who live outside the range of traditional networks. It might not look as janky as this, hopefully, but what I think the important point to take away is that this is an ISP that's building service using locally available resources in ways that are tailored to local needs. And this is a fixed line service provider, so they're actually providing fixed internet via Wi-Fi to people's homes and so forth. But like I said, cellular is really what matters today, particularly if we care about folks in kind of least developed countries. So even though very few people, particularly in rural areas, will have access to a computer, most people today now have access to a mobile phone, even if not all of them are using mobile internet. And so, whereas this is the example of Air 1 that I showed is a good representation of what a rural fixed operator could look like. There's also been a bunch of work related to community-based cellular networks that are actually providing cellular service to people's handsets, using similar techniques that are built by and for their users in many cases and often optimized similarly for local needs and leveraging local resources. And so this is where a lot of my research is focused. And so I've done a few different projects in this space around using dynamic spectrum to enable these networks, also doing some work now, like I mentioned before, on network planning and broadband mapping for these and other rural networks. But what I'll be focusing on today are lessons that we learned from a project that some collaborators and I worked on at University of Washington, University of the Philippines, for a large-scale community cellular deployment in the Philippines. So to start with, let's understand how cellular networks work today, so you can kind of get a sense of what were the challenges we were facing as we were trying to deploy this project in the rural Philippines. So hopefully many of you have seen cell towers before. This is the kind of user visible face of the cellular network. But cell towers on their own don't actually do anything to provide service. If you just deploy some radio equipment on a tower, you're not going to be able to start your own mobile network operator. You need to connect it to what's called a mobile core network. And the mobile core network is actually what enables you to provide service to end users. This is where you're going to implement billing and all those kind of interesting features. And what this means is once you connect these two together, you can actually start providing service to users. But even if you have two users on a single tower in a single rural location and they want to make a phone call to each other, for example, that traffic is going to go to your mobile core, which if you're a traditional mobile operator is probably going to be located in your national capital, for example, and that traffic will go back to the same rural community in that same tower to go to your next user. And this works. This is how those billions of people who are using cellular networks today actually how their traffic flows. But it has some shortcomings when we start to think about applying this system architecture to extremely challenged environments. So if this link goes down, for example, then you're completely out of luck. Say, for example, a backhoe comes along and rips up the fiber line that's connecting your tower back to the mobile core. Even though everything else is working in your particular community, you have no way to communicate with anybody in your proximity unless you go find them and talk to them face to face. Similarly, if something happens with the mobile core itself, say somebody botches an upgrade, then the entire network goes down, like for the whole country. And this, as we'll talk about later, still happens today all the time. And so one of the challenges with the way traditional mobile networks are built today is they don't really degrade gracefully in the face of failure. And as we'll talk about, it turns to be a really important challenge when we're building rural networks. And it's also extremely expensive to modify these mobile cores or even to get started with one. So at a previous company, we had to buy a mobile core to run some, do some kind of engineering development and prototyping, and it cost like $5 million to buy the core infrastructure you needed to connect a single base station using traditional approaches. It took 6 months to install. It was like 4 racks of machines. We had to like rip a wall out of the room we planned to put it on because an extra rack of machines showed up. So it's super expensive, and because it's so dangerous to modify these things, you can take down the whole network. there's very limited windows in which network operators actually want to make significant changes. So to, yeah.
Is the expense justified by what they provide to you, or is it just? No, I mean,
Yeah.
I
question.
didn't mean as a joke, but like, is the actual hardware that they're providing to you, is it like some kind of state of the art, super proprietary thing, or is it just like, we know we have you by the neck, and so
Yeah.
we're gonna provide you with this for $5 million?
Most of the cost is licensing in this case. Yeah. So I mean, the particular system that we had purchased, there's very few companies that make this, so it's one of four. I'll leave it at that. I think the pricing was under NDA, but you can guess. Most of the cost was just licensing. I mean, these are just standard Dell servers that everything's running on, and I don't want to. I want to say that for this particular project, we were trying to make a replica of a actually existing mobile operator's core network for a project we're working on with that operator, so we could actually test some of the integration points between our system and theirs. It's definitely possible today to buy kind of virtualized cores that are going to run on hardware that you have available that'll take up less physical footprint. There's work going on in industry to improve the situation, but at the same time, if you in 2018 when we went and deployed this is what it actually cost a mobile operator to deploy some of this stuff. So adoption can still be pretty slow. But to your point, I mean, most of the cost is licensing. So we built a system called Community Cellular Manager to kind of try to address some of these points. You can go look at it on GitHub if you're interested. And what Community Cellular Manager did, the kind of key change that we made is we tried to take this centralized core and distribute it as much as possible to the edge of the network. And the idea for this, we introduced kind of two new elements. We have a client that's going to be co-located in the community with the cell tower, sitting at the base of the cell tower. And all the network policies, so things like authentication, billing and charging, metering, how long you're talking on the phone, that kind of stuff is being implemented there. We retained a controller element that was running in a public cloud environment that would connect with a telco partner. They would be the ones who are actually allocating things like phone numbers to users, controlling what radio frequency spectrum these community-based networks are able to use. And if you needed to make phone calls that were connecting to the rest of the world outside of your particular community, that traffic would be routed through this controller. That was the physical path that existed to connect to the network. And this has some nice properties. You know, in this case, if we lose this particular backhaul link, obviously there's no physical path. You can't communicate magically to the outside world, but you can still continue supporting local communication within the footprint of a single client device. And similarly, it became really easy actually to update this controller because we were able to separate out the different functions that were responsible for control and management of the network from the very few number of functions that were necessary for actually handling voice traffic in and out of the network. So we can make upgrades in kind of a rolling fashion. It was pretty easy to do that. The other thing that was really cool is we were able to actually customize each individual community's network if desired. And so this will come up in a second, but you could actually have within the same controller instance, because each community was responsible for implementing the policy, or they controlled the hardware that implemented the policy for their network, they can make customizations without having to coordinate with the incumbent mobile operator. And if you wanted to say, go to AT&T or Verizon and say, hey, we're a municipality, we just built this tower, and we want to have special pricing for some of our users, they're probably going to laugh you out of the room, or they're going to require you to have a very different kind of structure for your business. It'll be a kind of a corporate commercial engagement between two operators, which turned out to be quite difficult to do. So we deployed the system across 17 sites for 3 years. It wound up handling during our study duration over 50,000 hours worth of calls, more than 3 million text messages. And we did this project in partnership with Globe, which was the #1 telecom in terms of subscribers in the Philippines at the time. And we had 2 different sets of sites. So some were directly managed by Globe and an NGO partner. These are the Globe sites in blue. And then also our partners at the University of the Philippines were working in a more hands-on way with a subset of communities to kind of deploy some of these research networks, if you will, in the northern part of Luzon. And this is what one of the networks looked like. So it cost about $18,000 to deploy one of these soup to nuts. $18,000 might seem like a lot, but compared to the cost for kind of traditional mobile networks, particularly in rural areas, this is like an order of magnitude less, though in theory, there's no reason why a mobile operator couldn't use something similar to what we were doing if they were willing to innovate a bit. is powered using solar power and batteries for power for the system. We would connect it to backhaul using a geostationary satellite broadband terminal. And the only real change that we were adding compared to what you need for the traditional model is a small computer that's run into the CCM client. So this is the only cost delta and power delta compared to the traditional architecture. And this costs about $300, like 2% of the total site cost. It's really not much. Yeah.
Out of the 18,000, what's the biggest thing?
So power entirely. So the access, and that's actually a really good question, because in many cases for traditional mobile operators, a large part of the cost is actually site acquisition. And so getting access to this little fenced off area and negotiating the licenses and agreements with the municipal government in the case of the Philippines, that is a huge cost. And not necessarily just the land, it's the process of going through that engagement. But when you put ownership in the hands of the community, like those costs kind of go away because it's the town government itself that's doing this. And so that's kind of one of the other ways in which community-based approaches can significantly reduce costs. Something that we saw with some of the communities that Globe was working in, actually, that I thought was really interesting, is they had assumed in their understanding of what the rural Philippines looked like from a power perspective, there's no power available that you can rely on. So you have to provide solar power as the power source for these networks. And what we found out during field work is that most of these communities had built their own essentially microgrids using diesel generators. And one of the ones that we had done some of our field work in had come up with this interesting approach where the barangay's government owned the generator, and you basically would pay per day to use electricity based on if someone would go around, if they heard the TV on, then you pay one rate. If they just saw lights on, you pay a different rate. And we laugh, but it's also like that's an interesting approach for like managing a shared community resource. And this generator could have easily provided the power needed for powering a base station, and that would say reduce this cost probably by half, from $18,000 down to less than 10,000 easily. If that community, if Globe had coordinated with the community to take advantage of this informal infrastructure that already existed. So these are, again, some of the dynamics that kind of emerge naturally with these community-based approaches.
Yeah, and were all these towers set up in areas that previously did not have service?
Yes. Yeah. Specifically, and I should note, these are all kind of 2G towers, so they're providing just voice and SMS, so no internet as well, and they were just providing those services. So one of the questions that we were asking ourselves as researchers, we put all this work into building this nice distributed core, and was it really worth it? So we wanted to look at what the uptime patterns were for this network and what are the types of outages people faced. And so this kind of each line here kind of represents a different site. The top ones were deployed by University of the Philippines. The bottom ones were deployed by Globe. And each kind of circle represents whether a site was online for an entire hour or not. And so you can see a few different patterns of outages here. So some sites have these intermittent outages, usually intentional, where sites would be shut down for the night and come online during the day. Some sites were consistently online. Some sites broke and had extended outage periods. But we kind of went through and looked at the total amount of time the system as a whole was operational, and it was only like 65%, which is pretty low for a cellular network, right? And we're curious, like, why is this the case? What's going on? And so for at the University of the Philippines sites, our partners there had basically categorized what the outage cause was for all the outages they experienced for a subset of the deployment duration, and kind of classified them into one of 5 categories. Backhaul could have gone down, you could have had power issues, and this was explicitly taking out planned outages. So again, communities that decided to shut their service off at night, that wasn't included here. And what it turned out is that about 42% of the incidents by duration were caused by backhaul failures, which is exactly the problem that we solved with our support for disconnected operation. And so the key point here is that in these rural networks, downtime is a constant factor you're dealing with. And if our median site uptime is only like 40-ish%, that's driven by factors that really are out of the control of the core side of the network. These are due to environmental factors, due to power failures or due to bad weather disrupting the ability for the satellite connection to stay up. And by supporting disconnected operation, we're able to create a more reliable and financially sustainable network as well. So compared to a traditional approach, during these periods of downtime, we're able to support continued operation of the network. And so this led to an increase of about 20% of more calls and SMS, and really critically, 16% more credit transfers. So 16% of the credit transfers that happened in the network were during these downtime periods where the site was up, but there was no backhaul available. And the transfers are important because this is how people would buy airtime on the system. You'd go to a shopkeeper, engage in an SMS-based transaction to hand over cash and get minutes that you could use on your account in the process. Some of our partners at University of the Philippines and University of Washington also built some really cool local services on just the subset of the University of the Philippines site. So one of my favorites was discussed in a paper at CHI in 2017, which was essentially a repair manual SMS app that they built that would essentially detect problems with the site and then send out broadcast text messages to community members saying, hey, there's a fault with the site. And if someone responded, it would walk them through troubleshooting and debugging steps to bring the site back online. And this is really cool, but it'd be very difficult to implement something like this if you had to coordinate with the mobile network operator to both get detailed information on kind of the operations of every individual site and also integrate that into a third party's research application. When you're able to work kind of directly with a community site, you can do implement interesting approaches like this. So all of this, I think, kind of captures our experiences from CCM, really capture or what I call kind of the systems approach to bowling for the edge. We were able to think about the broader context in which these networks were being deployed and think about why this population underserved, and then build upon kind of local aspirations and capacities to build a tailored solution that would work for the local conditions of these community networks. And this was super exciting and inspiring work for us. But some of you may be wondering if that's kind of niche. And yeah, these are 2G networks specifically for the rural Philippines. But my claim is that network systems built for the edge can inform how we build scalable, reliable, and evolvable networks like everywhere else. And so there's lessons from how we build these systems that turn out to be useful at the core as well. And so again, to see this example, we can look to telephony for a comparison again. So if we go back to the 1950s, this is what existed inside AT&T's network. This is a phone switch. There would be building-sized switches in major cities where all your traffic would go through. The equivalent in a modern mobile network, this is an image that Telefonica posted of one of their the data centers that runs their mobile core, looks kind of like this. And so while the phone network that we use today has changed a lot, we now have significant coverage of the world's population. There's more than 5 billion people and 20 billion devices in the network, huge amounts of traffic that are being sent over the network. Unlike the phone network, we support many applications instead of just voice. A lot of things that actually, I would argue, stay the same. You still turn on your phone, it connects to this piece of centralized infrastructure. That centralized infrastructure gets to decide what you can and can't do on the network. In most cases, if the phone company needs to handle more traffic or more capacity, they'll have to buy a new switch, as it were. In many cases, this is literally called a forklift upgrade because you were getting a forklift to bring the new racks into the data center to buy a bigger core. Or if you're upgrading generations, historically, that's required a complete replacement of your existing core network as well. And if the mobile core breaks, the whole network stops working. And like I said, this still happens today. We have many examples of nation scale outages because of a botched upgrade, a certificate expiring somewhere in the core network. And so if you think about some of the key challenges that mobile network operators face today, these are the most people networks that I'm going to call them, is they face a challenge around evolvability. How do they adopt new technologies without having to do these forklift upgrades? How do you minimize failure for critical services? And how do you cope with increasing user and traffic load as well? And I think rural networks can help inform many of the ways that we think about solving these problems. And so one of the first lessons that that's related to evolvability is thinking about how we modularize the access networks. These are the towers or the particular technology your device is using to connect to the network in that first hop. some of the observations that we can take away from rural networks is that all the traffic that matters, what people are actually doing on their devices, is just IP internet traffic. So they're communicating with their friends and family over things like WhatsApp, they're watching videos on YouTube, things like that. And it turns out that modern mobile applications are really good at handling flaky network connections because we're always using kind of Wi-Fi, or we're using cellular networks that work kind of most of the time. And they're far more reliable than the protocols that are built into cellular standards. And so the way that cellular base stations communicate with the core is extremely sensitive to latency and kind of flaky networks. So the implications for evolvability are that, if we can take these cellular protocols, these 3GPP defined protocols, and terminate them as close to the edge of the network as possible, we can just eliminate entire classes of failure mode. And it also means that we can think about how we can move policy enforcement to the edge as well. So if the only traffic that matters is IP, if we can enforce that our policies for the intent of the network operator at that edge, then the rest of the network becomes very simple because we're just moving users' IP traffic over whatever backhaul is available. The second big lesson is to try to limit failure domains. And so a failure domain is really answering the question, it helps us reason about the question as we're designing a system of when something fails, what is the blast radius in which it's going to affect. And so today, the failure domain for a mobile core is the entire country. And so in rural networks, as we discussed, components fail all the time for reasons that are usually due to environmental factors that are just kind of outside your control. You can't control where backhoes are going to cut your fiber. It's just going to happen, and your system should be resilient to it. And so the implications for reliability here are that we want to limit failure domains to the smallest possible size and design our systems for resilience in the face of failure. And to help us reason about doing this, we can adopt desired state models for thinking about how we manage how different components handle state within our network, which I'll talk about a bit more in a minute. And the last lesson is to think about how we scale horizontally. There's a diversity of organizations and business models serving these edge communities, like this photo here, which is from Air One deploying their first cellular base station, or some of the community networks that I talked about. And these are organizations that are building networks one node at a time, starting from zero and going from there. And so thinking about how we scale down so they don't have to make a $5 million investment at the start to start experimenting with these technologies to understand if they're going to be useful to them is just as important as scaling up. And so we want to be able to support heterogeneity and difference across and within the different networks that we're building, and allow these incremental deployments and experimentation below upfront costs. And so one of the projects that kind of built upon these lessons was one that Jen mentioned earlier, Magma, which is trying to take some of these modern principles and apply them to the mobile core. And in a lot of ways, the architecture of Magma should look familiar to what we talked about for CCM, but Magma is not just designed for these extreme rural edge cases, it's designed for supporting LTE, 5G, and XG cellular networks more broadly. And so Magma introduces this notion of an access gateway similar to the CCM client that exists at the edge. Conceptually, it's kind of co-located with the cell tower. It terminates all the 3GPP signaling. At that point, it outputs IP traffic over whatever backhaul is available. The way that we think about the network functions that are running on this access gateway is that their state, their runtime state, is a simple direct function of the configuration that's given to them by the element that I'll discuss next. And these generate, metrics for network monitoring and so forth. The orchestrator is this equivalent of the CCM controller that we talked about, and provides this management abstraction. It's a logically centralized service, could be running in a public cloud, it could be running in a data center, and it provides this durable and authoritative configuration state for the entire network. You can think of it as providing this big graph representation of entities and edges, where these entities are representing access gateways. And this is what operators configure. They configure the orchestrator, and then the software manages how that configuration gets realized across the network. Importantly, it's also not in the data path anymore. So there's no more kind of centralized elements in a Magma network for users' actual traffic. And these all simply kind of connect together over the public internet using whatever backhaul is available. To briefly kind of look inside the access gateway, you can kind of see how these services get realized. There is a whole set of modules that terminates these radio access network specific policies at the edge. So this can be LTE, it could be 5G, it could be Wi-Fi. Currently, it supports all of them. And then we have a set of services that are edge or access network agnostic as well, that allow operators to express their policies in a way that doesn't really matter what the technology users are using to connect to the network, since it's just operating over IP traffic. And so I would argue that Magma kind of points a direction towards a more scalable and reliable set of mobile networks. So the orchestrator is centralized, but it's not on the critical path anymore. So we've removed that single barrier or that single point of failure from the traditional networks. And these access gateways are, in a sense, decentralized from a data plane perspective and just rely on ephemeral runtime state. So they're access network agnostic because of the way we've modularized the network. The failure domain in this network is a single access gateway. So if one piece goes down, it doesn't really affect anything else. The core goes down, access gateways continue operating just as they were before. And the core capacity now scales horizontally with RAM capacity because you're adding core capacity as you add towers. If you start with one tower, you just add a small amount of capacity. As you expand, you can add more. And this enables some pretty cool tricks. So it enables things like rolling upgrades. So if you want to upgrade your core today, you upgrade the core and you hope you got it right. If you want to try out a change in a Magma network, only a small portion of the network is going to be impacted at any given point. It requires maybe rebooting a cell tower or something like that. You'll only lose coverage for that for the time that it takes to do that. We also have some cool tricks we can use to implement high availability. So a typical radio can actually connect to multiple access gateways, kind of as part of the standards for how radios work. And so in the default case, you can be connected to the access gateway that's located at your tower. And as a fallback, you can go and connect to an access gateway that may be provisioned with the same configuration state that's running as a backup in the cloud. And if for whatever reason your local access gateway falls down, your radio can simply fall back to using the one in the cloud until it can come back online. And so Magma is being used today to power some commercial networks. We talk about this in our upcoming NSDI paper. One that I think is particularly interesting is this network that's built by Access Parks, which is providing kind of fixed wireless service to Wi-Fi hotspots in state parks, national parks, places like that. As of when we published this, it had about 200 hotspots that were connected over Magma. And another really interesting one is Freedom Fi's network, which is at the time of writing, things have changed through some acquisitions, but was building the cellular network for Helium, which is kind of a cryptocurrency incentivized distributed wireless network. And they were able to deploy over 5,000 access gateways in less than 5 months across 45 states. And they're using this to build a neutral host network. So they are not actually providing service, or you don't go buy a SIM card or service from Freedom Fi. Mobile operators can allow their customers to roam onto this network. And both of these are very different business models and use cases, both supported by the same software. And adopting this approach also has some really great cost benefits. So according to Access Parks, it actually reduced their network costs by over 43%, largely due to the reduction in operational overhead that was required to go deploy individual radio sites at every single location they were working on, thanks to the way we kind of separated out the access gateway and the orchestrator. Another project that's been built on top of Magma that's also kind of looking forward is thinking about how we can embrace heterogeneity across MNOs. This is a project called Cellbricks. So a traditional MNO, you go to Verizon and you get service from them, you sign a contract, you pay the money. User management and billing is handled by the same organization that runs the actual network. And what we've talked about already is these networks don't cover everybody. And so there's other types of cellular network that are coming up today, thanks to the increased availability of shared spectrum, like CBRS in the United States, such as community networks or enterprise private networks. And your phone could connect to any of these, in theory. It has the technical capacity to do so, but it's not able to actually perform authentication with your home network unless you have explicit roaming agreements in place. And now we've reached a point where it's easier to actually like go home, like you could go right now for a couple $1,000s and build your own cell phone network, but it's easier to build that yourself than it is to get a roaming agreement. Just as commercial engagement with Verizon or AT&T, that could take years. And if it's just one tower, they're not going to talk to you. And so the idea behind Cellbricks, which is again kind of building on top of Magma, is to decouple this customer relationship from the network. So you might go get a contract from Verizon, but Verizon's no longer going to be operating the rest of the network. And I won't talk about the details here, but I'm going to go through more in our paper. But we kind of devise a new way of performing mutual authentication between a user, what we call a broker, who owns the commercial relationship with the user, and the network that you are currently trying to attach to dynamically kind of achieve trust across all of these and provide accountability for services. And as your phone moves across networks, even ones that your broker has never engaged with before, you should be able to also continue to receive service. So to wrap up, designing for the edge can inform the core. there's a lot of challenges with the way today's mobile networks work, both in extreme rural environments and in the environments like here, even in Princeton, or even in major cities throughout the world. And if you take nothing else away from this, I want to encourage us kind of as a research community to think about how designing for the challenges that rural communities are facing is actually valuable, not just for those communities, but also can give us lessons and expand the way we think about how we solve problems for networks everywhere.